Alright, so last time we discussed the two conclusions of satellite, right? We drew two conclusions for satellite orbits, okay, and then we draw equation for the speed and another equation for the period. These two equations, you need to know how to derive these two equations. Again, we derived them using this equation and the centrifugal force equation we learned before, and also the equation between the velocity and the period in a uniform circular motion. Right? You set them up, you just rearrange these two equations, you finish the algebra, then you can find these two equations for the V and T. You don't need to memorize these two equations. There's no point doing that in physics because they're just conclusions, right? So we finished that part. We started another part. We started to revisit these gravitational potential energy. Why? Because this equation we have been using is not valid anymore in this part when things are moving at a distance really far away from the Earth, comparable to the radius of the Earth, like the object in lecture 19, slide 1. Really far away from the Earth, this little g, first of all, it's not going to be 9.8 anymore, right? Secondly, it's changing all the time. So this equation, it's only an approximation. It's a very good approximation on the surface of the Earth, or very close to the surface of the Earth. But if it's far away from the Earth, we have to use this equation. This equation can be derived from the fundamental theory for any potential energy, any conservative force. We didn't derive that, so this equation will be given. So I believe these two equations, only these two equations are going to be given. Okay, the rest are just going to be conclusions from them, right? So when we use this equation, so whenever we need to calculate potential energy, gravitational potential energy in this part, okay, we just use this equation. Forget about that one. We don't use that one anymore, okay? Only in this part, in this chapter, gravity chapter, we're going to use this equation. And the only variable is going to be this little r. And remember, little r is the distance from the center of the planet or star to where the object is, right? This diagram explains the difference between little r, big R, and h, these three symbols we have been using, okay? If you understand what they are, you're not going to be confused by big R and little r, okay? All right, so as I said, then we can still use the energy method to make predictions in this part. Only the change is going to be, don't use this, just use this. Kinetic energy still 1/2 mv squared, okay? There's no change in that term, okay? Now we're going to take a look at an example, practice this more general equation we just learned. Lecture 19, slide 4. At Earth's surface, a projectile is launched straight up at a speed 10 kilometers per second. To what height will it rise? So basically, this is pretty much like a pre-fall problem, right? Something's launched straight up with a speed, right? I can throw something up with a speed, and then I want to find the maximum height it goes. Usually, we can just do, if it's free-fall problem, we can just use kinematics or conservation of energy. Remember, you can also use conservation of energy for free fall. Don't always do kinematics for everything, right? We have learned so many theories, so many laws, okay? These conservation laws, they are more powerful than kinematic equations. But first of all, you can't even do kinematics in this problem. Why? It's not like, it is free fall, but the acceleration is not 9.8 always, right? Think about this. It has a speed 10 kilometers per second. It's not 10 meters per second. 10 meters per second, well, it's gonna fall back really soon. 10 kilometers per second. It can go really high, much higher to above the surface of the Earth, then fall back, okay? So in this case, the acceleration is not always 9.8, it changes. So this is not a constant acceleration motion. You cannot do kinematics, okay? Then we can still use conservation of energy, okay? Conservation of energy doesn't care if the acceleration is constant or not. Set up an initial and final. Put numbers in. Rearrange this equation. You can find things you need. Right? So let's still do that using conservation energy, right? So this is still something with an initial velocity. It's going to go really, really high. That's fine. I'm just going to find this maximum height, right? Now I'm going to set up conservation of energy using this term, not the MGH, right? So let's do that. I'm still going to do delta K plus delta UG. Now, of course, no work, right? Because only gravity is on this object, right? This is still like a free fall with initial velocity. So, and gravity is always on the left-hand side. Gravity never goes to the right-hand side. It's not from the outside, right? Because the right-hand side is external work. But gravity doesn't go to the right-hand side. Now let's set it up. This guy, the same. No change. Final minus initial. And there's only one object here, right? The projectile. Now the gravitational energy, you're going to use this term. So you're going to carry this negative sign. You don't drop this negative sign. There will be a lot of negative signs here. Be careful. You're going to do final. Which symbol is going to have a subscript final? This. This is the only variable now. Final minus initial minus, okay? This whole thing is the initial. There's a lot of negative signs here, but I'm just using the definition, right? I'm not making some actual negative sign. This is the change in potential energy equals 0. That's the only difference. That's the only difference, right? Now let's see. What do we want to find? We want to find what height you will rise. So we want to find maximum height, which is just the H final. But this problem doesn't have H final. Remember, this explains the relation among these three variables. We can first find this final R, final distance from the center to the Earth. And then, if you want me to give you the height, I'm just going to subtract this radius from that, right? So I can still find RF, and then at the end, HF is going to be equal to RF minus the radius of the Earth. Okay, don't forget that step, okay? Because the problem only asks you to what height will it rise. Okay, you don't include the radius of the Earth. Okay, so I'm going to still solve this problem to find RF, because I can only find RF in this equation, and then subtract the radius from the Earth. Okay, what numbers do we have? Final velocity is going to be 0, right? Because you want to find maximum height. So yeah, it goes really high, but at the top, still the velocity is 0. So this is 0. Now you would say, then what about the initial? Usually we assume the ground is the initial 0 height. So can I cross this out? First of all, you don't have an initial height here. Secondly, which one is 0? If you assume this is 0, then this term becomes infinity. Doesn't make any sense, right? So you're not talking about height here, you're talking about distance from the center. What is the initial distance from the center to the projectile? Initial distance from the center of the Earth to the projectile. That's this, right? So the initial R is at the surface, okay? Initial R is not 0. You can say initial height is 0, but I'm not plugging the initial height in that equation. I'm plugging initial little r. Little r is the distance from the center of the Earth to where the object is. So that means little r here is going to be the radius of the Earth, okay? So I would have these two, and then this is negative sign. There is a negative sign. Now this guy becomes positive, right? Because there are two negative signs, G, M, little m. This is going to be the radius of the Earth, because the initial distance from the center is the radius of the Earth. It's not a 0. The height is 0, but this is not the initial height. Okay. Now you see that. Okay. Now we can do that, right? Because we have all the so VI. 10 kilometers per second, convert it to meters per second, right? You can't use this number. So you're gonna do 10 to the 4th meters per second. That's the VI you're gonna use, right? Now we can also cancel little m, right? Each term has a little m. Each term has a little m. You can cancel that. You just divide both sides by little m. Right, so what do we get? We're gonna get negative 1/2 VI squared minus GM RF plus GM, the radius of the Earth, equals 0. Don't forget what we're doing. We're trying to find RF, okay? So let's move this term to the right. So I would get negative 1/2 VI squared plus GM equals GM by RF. Now you're ready to plug numbers in, right? Because you have this GM radius. This will be a number. This will be a number. This will also be a number, right? Then all you need to do is this, right? At the end, I'm going to erase this, okay? At the end, you will get the RF. It's just going to be G big M divided by this whole thing on the left. But this is just going to be a number. You plug numbers in, you will get a number there. Plus GM. All right? So then you can plug numbers in, find the final answer, right? You already have all the numbers. VI converted to meters per second, big G constant, mass of the Earth, radius of the Earth. Put all the numbers in carefully. Again, I would calculate the denominator, calculate the numerator, and then pick these two numbers from my calculator, enter. Don't enter all the numbers once, okay? All right, do the algebra carefully. This RF, you're gonna find it's gonna be this. Okay? Some people, they will stop here. This is not the height. This is only the distance from the center to where the projectile is at the end, at the maximum height, right? But the problem doesn't ask you this total. The problem says, I want the height. I want the height. Okay? Subtract the radius of the Earth from it. Subtract the radius of the Earth from it. That's going to be C. C is the right answer if the problem asks for the height, only the height, not the distance from the center. Okay? So this is this problem. Now we're going to take a look at another one, slide 5. We're going to practice this new term again, still energy method. A 470 kilogram communication satellite is in orbit 280 kilometers above the surface of the Earth. What is the total mechanical energy of the satellite? Okay. Total mechanical energy, as I said, mechanical energy is just a name for the sum of kinetic energy and potential energy, right? You can take a look at the slide 3. I listed it there. It's just a name. It's just the sum of the kinetic energy of the potential energy. Okay, so the problem just says that find the kinetic energy, find the potential energy, add them together. You don't even need to use a law, right? Just use the two definitions, okay? So now let's see. Okay, now I'm going to erase everything. What is the kinetic energy? Well, kinetic energy, you can find it this way. Because kinetic has a definition, right? 1/2 V squared. Okay? And gravitational energy, plug numbers in this equation. Don't remove this negative sign. Don't. Okay? So the total mechanical energy is just going to be this number plus this number. This number plus this number. You will get a positive number plus a negative number. Okay? So let's see. If I So if I have all the numbers ready, I will just plug them in, right? So let's see, what do we have? We know the mass of the satellite. Okay, good. That's little m. I do have little m. Big M is the mass of the Earth, right? It's still orbiting the Earth. G is the number, right? I don't want to do anything here. G is the constant, okay? Big M is a constant. So these three guys at the top, you don't need to worry about them. You already have them. You have the height. Again, you only have the height, right? If you want to find the R, the total distance from center, you're going to do radius of the Earth plus the height, okay? But you will find this R. So you can calculate this number first, right? Negative, keep it negative. V, but the problem doesn't tell us V. So you need to find a V, right? A lot of people, they were like, what do I do? Okay, I don't have V. I don't know how to solve this problem. Okay, so there must be a theory we can use to find a V first, then we plug numbers in, right? This is a satellite. What did we learn about satellite last time? Well, we derived the two equations for satellites, the V and the period. Wait, we derived the V. We derived the V last time. We have a theory for the velocity of a satellite orbiting the Earth, right? How did we derive that? Because when the satellite is orbiting the Earth, gravity is the centrifugal force. So you use the gravity equation, calculate the number, use the centrifugal force equation, calculate the number, equal them, they should be the same number, right? Then what we did is that I just use these two expressions. I find the expression for the V, which is this. Now you see that I don't have the V for the problem, but I can use the theory I learned for satellites, only for satellites, right? To find a V. Why? Gm, the constant, R is this R. It's still the distance from center to the Earth, the center of the Earth to the satellite, right? So I will find all the numbers I need. Then I plug numbers in, okay? Okay? It's not always, every problem is just like one step. Okay, so that's what we're going to do. But before that, actually, we can make things a little bit easier by working with the symbols first, right? That's always what I recommend. If I want to find the mechanical energy, total mechanical energy, I would do 1/2 mv squared plus this number, which is just going to become negative. This number isn't negative. Now let's plug this in, okay? Instead of finding all these numbers first, I'm going to first plug it in. And then V squared is just going to be Gm divided by R. Right? And then minus Gm R. And now you realize that they are almost the same term, right? The only difference, this has a factor 1/2. Okay? So if you factor it out, you actually get 1/2 minus 1 times Gm R, right? Because this is 1/2 times this thing. This is -1 times this thing. And 1/2 minus 1 is 1/2, -1/2. So at the end, you get -1/2. Okay? You see that instead of calculating these two numbers, they add them. You do the algebra with the symbols first. You get a very simple conclusion. Then you just plug numbers into this conclusion, right? So at the end, I get this. Again, this is not something I need to remember. Otherwise, you're going to be confused. There's so many conclusions you need to remember. No, I'm still just using the definition of kinetic energy, definition of gravitational potential energy, and then I make use of that theory. I will always find the right answer, always. Okay? So at the end, you do the algebra first with symbols. Before you plug numbers in, you get a very nice final expression. So now let's just plug numbers in here. You see, you will get a negative number at the end as a total energy. That's fine, because this potential energy is negative. And the number is even greater than the kinetic energy. You're doing like 5 joules of kinetic energy, -10 joules for potential energy, you do 5 plus -10, you get -5, of course, right? Because the potential energy is negative. You get a negative number at the end, okay? Now we can just, so the only thing we need is just going to be R. The only thing we need is just going to be R, right? And what is R in this problem, okay? It's going to be the radius of the Earth plus the height of this satellite, 280 kilometers. So that's just going to be 280. Okay, that's the R you're going to plug in, right? You plug all the R in. At the end, you will find the number, okay? Okay, so all you need is big G, big M. Little m is the mass of the satellite, right? And the R, it's going to be that number, okay? You plug all the numbers in. Please do that. You get E. Negative number, leave it there. The total energy is negative. That's fine. That's fine. Okay, don't freak out when you see negative energy. Okay. All right. So this is this part. Now we're gonna take a look at a second part. So this part we didn't even use conservation of energy, right? We just used the definition of kinetic energy, potential energy. We also just made use of the satellite theory. Okay. Now the next part, slide 6. Okay, the same satellite orbiting 280 kilometers, a rocket engine boosts it into a geosynchronous orbit. What does this term mean? It means it remains over a fixed position on the Earth. How much work does the engine have to do? Okay, we're finding work. Again, doesn't matter how complicated this problem is. If you ask me to find something, the first thing I would try is the definition. Everything in physics has a definition. Speed, distance over time. If I want me to find speed, the first equation I would try is the definition. Okay, if it's not that simple, I may need to use a law, theory to connect it to something else, right? Like conservation of energy has speed in it. If the definition doesn't work, maybe I can use conservation of energy. Kinematic equations have speed in it, so maybe I can use kinematic equations, right? But the first thing I would try is always the definition, easiest one. What is the definition of work? We learned that, right? Force, displacement, cosine theta. But it's not going to work in this problem because, first of all, it doesn't even tell you the process, the detail of the process. It doesn't tell you any force, any displacement. You don't even know if it's going to be a straight line or anything. You can't even draw that. So you don't have you have nothing here. Force, displacement, theta, no. So that means the definition doesn't work. This is not a simple problem. You just plug numbers in the definition. So now I'm going to connect it to something else, right? If I want to find acceleration, I do F equals ma. That's one way, right? I can connect it to force and mass. If I can find the net force and mass, then I divide them, I find acceleration, okay? So can you connect the work to something we learned? Work is always related to energy, right? So if I can do this, right, now we can use conservation of energy. I'm trying to find a work from the engine. So the engine is doing, or from the engine is doing work to the satellite. So it is work from the outside. I can't find the work using the definition. What if I can find this? If I can find the change in the total energy, then that's going to be equal to the work, right? So you see that now I'm using a law to connect this thing I want to calculate to something else that can be calculated easily, okay? So that's my strategy. I'm just going to calculate change in total energy. How do I calculate change in total energy? I would just do change in kinetic energy plus change in potential. But we just calculate total energy in the first orbit, right? So I don't need to do that. I don't need to work with 4 terms. So this is going to be initial, right? And the initial is this, okay? So all I need to do is just use these 2 terms to calculate the final total and then subtract them. Right? Because this is basically the change in the total energy, okay? So that's what I'm going to do. So I'm just going to calculate E total final, and then at the end, do final total energy minus initial total energy, that's just going to be this, right? And that will be equal to the work. Changing energy is going to be equal to the work from the outside, conservation of energy. Now, how do I find the initial energy I just found in the first part? So easy, I just need to find this guy. And then all you need to do is just use the definition, right? What is the final total energy? Final kinetic energy plus final gravitational potential energy. And again, as I said, if you repeat this, because V of a cell light is always calculated this way, and then you can repeat this, and then you will find, okay, I will get a very simple expression for the final kinetic energy, which is the same as the initial total energy, right? So that's the final total energy, the expression. So all I need is gonna be the RF, the distance from the center to the orbit, to the satellite in the second orbit, whatever it's called, a very weird name, geosynchronous, okay? So that's my goal. I need this number that I can plug in, find this guy minus this. So how do I find the RF for the second orbit? The problem doesn't tell me anything about it, right? The problem only says, okay, it's going to boost it into that orbit. What is that orbit? The meaning of that word? That means it remains over a fixed position on the Earth, okay? So that means when it's spinning, when it's rotating with the Earth is spinning, right? Okay, so say this is west, this is east. The satellite is also rotating with the Earth at the same rate, so that it's always going to be over the same point, right? Say it's always over Winston-Salem, but the Earth is spinning. The satellite is also rotating with the Earth at the same rate. So if I look up, then I will always see the satellite right above me. So you're just going to make sure in the second orbit, the satellite is just going to orbit the Earth with the same rate the Earth rotates about its own axis. So how do I use that information to find the radius? Okay, let me ask you this question. If the satellite is going to rotate with the Earth at the same rate, what will be the period of the satellite? It's going to be the same period of the Earth rotating about its own axis. That's how it's going to rotate the Earth, orbit the Earth with the same rate of the Earth, right? What is the period of the Earth rotating about its own axis? 24 hours, 1 day, right? So that means this information actually tells us that the period, okay, is 24 hours. So the final period is 24 hours. But that still is not what I want, right? I want the distance, the final distance from the center. Again, this is a satellite. What did we do last time? We derived two equations, the velocity and the period for a satellite. Wait, we derived the velocity and period, okay? So again, I can make use of that theory, okay? We derived that. How did we derive that? I make use of this, V equals 2 pi r over period. You do the algebra carefully, you will get the expression, okay? That's the expression we got last time, so let's take a look at that. You don't need to remember that expression, but you need to know how to derive that, right? So that's a very long one. 4 pi squared r cubed divided by gm. Okay, that's what I'm going to do. I'm going to use this equation, plug in the period, rearrange this equation, find the little r. That's going to be the little RF I plug in. Then I use this equation, then subtract these two energies, okay? So let's do that, okay? I want you to, again, pause the video, do the algebra yourself. This algebra is already lengthy, a lot of signs, a lot of scientific notations. So in this part, a lot of people make algebraic mistakes. It's not because they don't know the theory. It's just there's so many ridiculous numbers, negative signs, okay? All right, so I'm gonna So I'm going to need that. Okay, well, I'm going to erase this. I don't need this anymore. Because all I need is this. This is the E total initial. Right. Alright, so first of all, I'm going to rearrange that equation to get expression for RF, R, right? So how do you rearrange that equation? Well, first of all, I don't like square root. Square both sides. You get rid of the square root. Now, I don't like denominators. Multiply both sides by the denominator. You get g m t squared equals 4 pi squared r cubed. Right? And then you see that I'm trying to find r. I want to find expression for r using t. Divide both sides by 4 pi squared. You got r cubed only, right? And then just take a cube root, right? Cube root. Okay? Now you can plug numbers in. G constant, mass of the Earth, period. Convert this to hours, to seconds. So you're gonna multiply this by 60 and 60, right? Becomes seconds. Now that's the number I plug in, and then 4 pi squared cube root. Don't forget the cube root at the end, okay? So if you do everything carefully, okay, the R I get, that's the R. So the RF I get 4.23 times 10 to the 7th. Okay, write it. So this is the initial energy I need. So I just found RF, it's going to be 4.23 times 10 to the 7th meters, right? And this is already little RF, so I can just plug in. This is not height, right? Then you would get the total final energy using this expression, negative sign, 1/2 GM divided by RF. This number I got is negative, you will still get a negative sign. Okay, but this is not the number we're looking for. We're looking for the work. How do you find the work, right? The external work from the engine, now in this case is the engine. It's going to be the total energy final minus the total energy initial, right? What is the number you got? What is the right answer? The right answer is D, okay? So this number is D. Okay, at the end you get the, you should be very careful. And the work is going to be positive, okay? Makes sense, because if the engine is doing negative to a cell light, what's the point? Okay. Okay. All right. So that's this question. Okay. You see that we're still using the same law. We're still using the same law, but the problem with this, right? You're going to use this equation, and this equation. First of all, the R is the distance from center. Okay, so sometimes you need to find it, okay, using the height and the radius, okay. And if it's a cell light, you can also use those two conclusions we drew last time to connect the R with the velocity and the period, right. Then you still use conservation of energy to find things you need, right. So in this case, we find the work from the engine on the satellite by using conservation. This is still conservation of energy, right? The work from the outside equals the change in the total energy. All right. So I finished this question, and this is a very good exercise. And then raising a satellite So that's how you read the satellite. But in real life, reading a satellite is really complicated. You don't just like shoot it straight up, right? You see that slide 7 explains how to read the satellite, okay, in real life. So it's really complicated. Say the satellite is first in orbit 1, okay? So you don't just shoot it straight up, okay, and then change the orbit. You're gonna first apply a force. The thrusters are turned on, the rockets are turned on at point 1 to apply a force tangent to the circle. Then it's going to go into an elliptical orbit. Okay, once it goes to an elliptical orbit, so it's going to go to a point which is far away from the first orbit. Okay, which is farther away from the first orbit, and then at that time you're going to turn on the thrusters again to apply force, increase the kinetic energy and the velocity until the V matches this value, because the V is always going to be connected to the radius of the orbit, right? Once the V reaches that value, and then you can shut it down, then this orbit, this satellite is just going to stay in that orbit, right? Because once it has reached the velocity, that's always going to be the velocity in that orbit. Okay, so that's how you raise a satellite in real life. Okay. All right, so we just finished this problem. So now let's take a look at what we want to discuss next. The thing we want to discuss next is the escape speed or escape velocity. Okay, we know that if I throw something up, right, at the end we fall back to the ground because gravity is going to always pull it back. So we just saw a problem. If you launch a projectile at a very large speed, it's going to go really, really high, right? It's going to really, really high. The number we got was 10 to the 7th meters. So imagine there's a projectile can be launched with an even higher velocity. So it can go even higher, even farther away from Earth. At the end, it can escape from the gravity of the Earth, right? So there must be some minimum velocity in order to escape from the Earth, right? And you can find that minimum velocity again by using conservation of energy and this theory. So let's do that, okay? So how do I find the initial the velocity? So again, this is something you need to know how to derive, but it's still conservation of energy and this theory. So let's do this. So take a look at the image on slide 8. Okay. So something starts from the surface of the Earth. So I'm going to use this as the Earth. Okay. Something starts from the Earth, and then you want it to have a very large speed from this point, and then you want it to go really, really far away. Okay, escape from the Earth. Okay, from this point to even out of the solar system. Okay. Now let's apply conservation of energy. This is I. This is final. Okay. So let's do this. I still apply conservation of energy. Final delta K is 1/2 m final square minus 1/2 m VI square, right? And then plus changing gravitational potential. This is the term you use. Final minus initial. Now let's see. Okay, so I'm going to rearrange this equation. So initial speed is at this point. So I want to find the minimum speed it can get. It needs in order to fly to very far away from the Earth. So if it's really far away from Earth, that means RF is almost infinity, right? Very, very far away from Earth. Very, very far away from Earth. So the final point, this guy is going to be almost infinity. If this is almost infinity, what is this term? 0, right? So you will get this 1/2 m VF squared minus 1/2 m VI squared. Now this term goes away, so you will have another positive term, GM. What is the initial RI? Well, it's at the surface of the Earth. So that's going to be the radius of the Earth, right? Equals 0. Now let's rearrange this equation. I want to find an expression for VI, right? Remember, we're working with VI. I want to find the VI. So just move the second term to the right. You get 1/2 mVf squared plus gm over radius of the Earth 1/2 I squared. I want to find the minimum speed of VI so it can reach infinity, right? Which can satisfy this equation, because I already used the fact R alpha equals 1. So I want to find the minimum value of this guy. Take a look at the left-hand side. So that means all I need to do is just find the minimum value on the left-hand side. What is the minimum value of this guy? Well, this guy doesn't change, right? G constant, mass of the Earth constant, radius of the Earth constant, the mass of the object constant. So it totally depends on the minimum value of this term. This is the velocity of the object at the final point. What's the minimum value of this term? The minimum value is just going to be 0, right? So when it's here, it's almost like at rest, okay? It flies very far away, but at that point, the minimum value of speed is going to be 0. So if this is 0, the minimum value of this is 0, then you will get equals, okay, you just rearrange this equation. You see, we started with 4 terms, but at the end we get this term. And rearrange this equation, what do you get? You will get this VI equals this. And then everything is going to be constant, right? Everything is going to be constant. Everything is constant because this is big M, this is big R. So this is the escape speed or velocity from any planet or star, okay? So, and this is always going to be constant if you're talking about the same planet or star, because everything is constant here, okay? Again, this is not something to remember, but you need to know how to derive it from a conservation of energy, right? Okay? To find the minimum. If this is the minimum speed in order to escape from the planet or star, we just call it escape speed or escape velocity. Okay? So don't confuse this equation with this. Some people, they will confuse them. This is the equation for a satellite. A satellite does not escape from the Earth, right? A satellite is still orbiting the Earth, okay? This is the escape, and then this velocity does depend on where the satellite is, because this little r is changing, right? It depends on the height of the satellite. So that number is changed. Even though you tell me a satellite is orbiting the Earth, I would say where it is if you want me to calculate velocity. This is the escape speed from the surface. This is always a constant for any planet or star. Okay, if you want me to calculate the escape speed from the Earth, I don't need you to tell me anything else. I just need the mass and the radius of the Earth. Okay, so don't confuse this equation with that. That's for satellite. Very similar, but that's for satellite. This is for escape speed. This is going to be constant, but that thing depends on the location of the satellite. All right, I'm going to stop here for this video.